Hello, my name is Ashutosh and I'm the teaching instructor for NPTEL's Fiber Optic Communication Technology under Professor Deepa Venkitesh. Today we'll be discussing some of the assignment questions that are there. So here you can see that the first question is a standard G652.D step index fiber. So G652 is a standard in the ITU, and step index fiber gives you the profile, refractive profile of the fiber, and it has also given certain parameters, like this is the core radius 8.2 micrometer, fiber type single mode. So this is in the sense telling us the V number is below 2.404. Refractive profile is step index, N1 at 1310 is 1.4, N1 at 1550 is 1.468, and delta n is also given here. Delta n is N1 minus N2 divided by N1, so it is just normalized. Now the question is, find the value of V number and then use V to find the spot size using Marcus's relation. Now let us see how we can find the V number. We know V number is 2 pi a by lambda n1 square minus n2 square. Now in the question it is given that delta is equal to n1 minus n2 by n1, which is given out as 0.001. This can easily be rearranged. Delta n1 is n1 minus n2, or n2 is n1 1 minus delta. Now this is reasonable because the outer diameter, so this is like you have n1 here in the fiber and your n2 is around it, and for total internal reflection n2 has to be less than 1, which can be seen here that n2 is n1 multiplied by 1 minus something. So this entire factor is smaller than 1, so n2 is smaller than 1. Now we can directly substitute this in our V relation here. So it is given that V is equal to 2 pi a by lambda n1 square minus n2 square. Let us just do the simple algebra. From the simple algebra we get 2 pi a by lambda n1 square minus substituting equation 1, which is n1 1 minus del whole square. Now this can easily be written as 2 pi a by lambda n1 square 1 minus del whole square, and this is 1 by 2, or let me do it this way. This whole thing is under square root. If this whole thing is under square root, I can pull this n1 out, so this would become 2 pi a n1 by lambda 1 minus 1 plus lambda square minus 2 lambda 2 delta, which is 2 pi a n1 by lambda. This one goes away, so this gives me 2 delta minus delta square. Now it is given, what is given to us, it is given that delta is 0.001, therefore delta square is equal to is much less than 1, so we ignore it. And that would make our V relation, BV relation 2 pi a n1 by lambda under root 2 delta. Now let us substitute the numbers. So the first was The first question was find the V number at 1310 nanometer. After we have simplified this relation, let us just simply look at all the parameters. Lambda is equal to 1310. What is it? 1300 nanometer. No, it is 1310 nanometer. N1 is given as 1.4676. Radius is given as 8.2 micrometers. And what else do I need? Delta is given as 0.001. And I guess that's about it, right? I have A, I have N1, I have this. So let's just substitute it back into the equation and we get 2 pi 8.2 into 10 raised to the power minus 6 into 1.4676 divided by 1310 into 10 raised to the power minus 9 into 0.001. Now you might need a calculator to solve this, but after you do, you should arrive at the number something like 2.581. Is this the correct number? 2.581, yes. So your V number is 2.581, which is greater than 2.404. So in that case, this is not a single mode fiber for this wavelength. Now we have this. Now let us look at the spot size. Using Marcus's law. Now Marcus's law is an imperial relationship which relates the spot size, which is often represented by omega as 0.65 plus 1.619 by V raised to the power 1.5 plus 2.879 by V raised to the power 6 into A. And when you solve this, it should give you something about 8.61 micrometer. Now the second part of the question is repeat the same question above for 1550 nanometer. So what changes for the 1550 nanometer? What changes from the previous case? Lambda nu is 1550 nanometer. Now as the wavelength has changed, the refractive index has changed as well. So N nu has changed as well, and now it is 1.4682. The rest of the parameters remain the same. Now it is fairly obvious that the radius will not change. The A will not change because it is a physical dimension. But here we are also assuming that whatever is the percentage change, a relative change between N core and N cladding is still delta. This is what these assumptions mean, and using that, if we substitute back into the V number, which is 2 pi A and 1 by lambda, this time it will be 2 pi, this is still 8.2 into 10 raised to the power minus 6 divided by 1550 into 2 delta, which will give you a number of 2.182. Similarly, the omega can be calculated. Yeah. Omega naught, sorry about that, omega naught can be calculated using Marcus's law. Now let us look at the next question. Next question is the assignment 6, and it starts with using the given data below for question number 1 to 6. Now 1 to 6 is the same numbering in the question that is followed there in question number 6. A is given to us as 2.3 micrometer, N2 is given to us 1.447, and del N is 0.075. And this is the V number, this is the BV prime, and this is the VBV double prime. This would be helpful later. And the first question is, before we get into that, let us talk about dispersion a little bit. Now in the lecture we have seen that there are two kinds of dispersion. One is waveguide dispersion. That is the dispersion due to the shape of the waveguide. Second is material dispersion. Dispersion due to inherent choice of material. Now that we understand that there are these two kind of dispersions, one is waveguide dispersion and the other is material dispersion. The only way I'll be able to make a change in the material dispersion factor is just by changing the material itself. So that means that I'll have to dope it with something else to change the material dispersion itself. However, I have more flexibility. When I look at waveguide dispersion, because in waveguide dispersion I can tailor the waveguide such that the dispersion is different. What I mean by that, let us say we have a fiber in cylindrical symmetry. This would have some dispersion if I start having rectangular waveguides that you might have studied in your EMT theory. This would have different dispersion, and the shape of these waveguides can determine what is my waveguide based dispersion. So ideally we are limited by the amount of elements that we have and the doping processes that allow us to make fibers. So material dispersion is not something that we play with often, but waveguide dispersion is often utilized to tailor our dispersion requirements. Now the first question is, find the material dispersion and waveguide dispersion and total dispersion. So if I have my waveguide dispersion is Tm, my material dispersion is Tm, and my waveguide dispersion is Tw, my total dispersion is just the sum of both of these. Now it is given that dispersion at lambda naught 1540 nanometer, and we are given the first derivative and the second derivative. Now this is strictly can be done with the choice of formulas, but before we get into that, let us find the V number, because the V number is not given to us. So and V number will be used later in calculating some of these dispersion parameters. So we had arrived at the relation. We know that V is equal to 2 pi a by lambda n1 square minus n2 square. Now in the previous question, the one that we solved some time ago, it was given n1 minus n2 by n1 is delta. So we had simplified this such that n1 minus n2 is equal to n1 delta or n2 barabar n1 1 minus delta. Now, and in that question I was given n1 and delta, whereas in this question, if you see in this question I am giving n2 and the delta there. So I'll have to rearrange this a little bit, but this is still basic algebra. P is equal to 2 pi a by lambda. So this becomes n2 by 1 minus delta whole square minus n2 square 2 pi a by lambda. I can take n2 out again, and then this, my relationship becomes 1 minus delta whole square minus 1. Now this can easily be solved as, and move this to the side because I will need the room. 2 pi a n2 by delta 1 minus 1 minus delta whole square 2 pi a n2 by lambda 1 minus 1 minus lambda square, not lambda square, delta square plus 2 delta. This and this goes away, we ignore this, and then we are left with 2 pi a n2 by lambda 2 delta by 1 minus delta whole square. And ideally, if you are still doing small angle approximation, a lot of these terms, like this term, can still be neglected, and when you substitute values back into this, you would get 1.67 or something like that. Now if we go and look at the data sheet again, 1.67 is more closer to 1.7 than it is 1.6, so we will be considering these parameters. Okay, now let us calculate the material dispersion. Now this is strictly the approximation of formula dm, which is material dispersion, is given by the formula minus lambda by c d square n by d lambda square. This means minus 1540 nanometer by 3 into 10 raised to the power 5 into 10 raised to the power, so speed of light is 3 into 10 raised to the power 8 meter per second, but in fiber it is often that we deal in terms of kilometers, so it will become 3 into 10 raised to the power 5 kilometer per second, and we can directly use the value of dn square by d lambda given in the question, which is minus 0.03 per micrometer square into minus 0.003 micrometer inverse. Now when you solve all of this, you can either have it in the scientific notation, the way it is done, like, yeah, what I'm trying to say is that when you solve all of this, you can either transform this nanometer into 10 raised to the power minus 9, this kilometer into 10 raised to the power 3, micrometer into 10 raised to the power minus 6 whole square, or it would be easier if you do it in terms of picosecond per nanometer per kilometer. It would become obvious when we do later part of the question, and when we do these, you arrive at a number of 1.41 picosecond per nanometer per kilometer. This is a simplification. There are two negatives here, they cancel out, and when you just do basic arithmetic, you will arrive at the number 15.41 picosecond per nanometer per kilometer. The reason I have done this way will become apparent in the next questions that we solve. So this was the material dispersion. Now let us look at waveguide dispersion. Waveguide dispersion is given by minus n2 by c delta 1 by lambda, the V number, and d square bv by dv square. Now this is the second term in the table itself. Let us just start putting the numbers in. We have minus 1.447 divided by 3 into 10 to the power 8 into 0.0075 divided by 1540 into 10 to the power 9. We've chosen this to be 1.7, and the BV value is 0.785. Now when you solve this again, it would come out to be 31.34 picosecond per nanometer kilometer. Now if I have these two, my total dispersion would be d material plus d waveguide, I'm calling it dt, is equal to 15.41, and this comes with a minus sign. 15.41 minus 31.34 picosecond per nanometer kilometer, which gives you minus 15.94 picosecond nanometer per kilometer. And this was the extent of the first question. What did we do in the first question? We found the material dispersion and the waveguide dispersion, and the total dispersion was just the sum of these. We used the parameters given to us in terms of the table and the n to calculate the closest V value. I will move on to the second question. The second question is related to the data collected in the first part. We have to find beta 2 at 1540 nanometer. Now we know beta 2 is given by minus d lambda square by 2 pi c, and we have calculated. Now this d here is the total dispersion, so we calculated it to be 15.94 picosecond per nanometer kilometer into 1540 nanometer whole square divided by 2 pi into 3 into 10 to the power 8 meter per second, or 5 kilometer per second. When you solve all of this, it will come out to be, if my math is correct in this case, 2 into 10 raised to the power minus 26 seconds square per meter. So this is the answer in this case. So this was a simple arithmetic question here. All that is expected of you is to recall the relationship between the GVD and the dispersion coefficients. Yes. Now the question here is, find the accumulated dispersion per nanometer in this fiber if the length is 100 km while operating at 1540. Now this, the accumulated dispersion can be calculated as dl lambda, where d is the dispersion, this is the length, and this is the spectral width, which in this case I will assume to be 1 nanometer. And now you will understand why it was easy. So we calculated the dispersion to be minus 15.94 picosecond per nanometer per kilometer, and then I am given a 100 kilometer length. and this I will assume to be 1 nanometer, the spectral width of my pulse. So this and this easily cancel, this kilometer easily cancels, and then what we are left with is it 100 kilometers? Yes, it is 100 kilometers. And after this we are left with minus 1.594 nanosecond per nanometer. Oh, yes, this, sorry about that. This nanometer comes here because in the question it has asked me to calculate per nanometer, so I should not be multiplying it with a nanometer. Whatever I am calculating is per nanometer, and that why this nanometer is left here in this case. Move on to the next question. Now the next question is find the accumulated dispersion for a 10 gigahertz NRG system at 1540. So in the last question, that is question number 3, we had calculated per unit accumulated dispersion, because we did not know the spectral broadening. However, in this case we are given a 10 Gbps NRG signal. So a 10 Gbps NRG signal, what it will do to a perfectly square wave around mega naught, this is like your 193 terahertz central frequency. What it will do is it will broaden it out. Okay, so 10 gigahertz this side, 10 gigahertz this side. Actual spectrum, I might pull it up next week. If you do a power spectrum, it would have looked like this. There would be smaller side lobes present as well, because this would be like a sinc function. But this gives me my spectrum. So most of the power you can, now this is just a matter of convention. You can have that, oh, I will consider till the first lobe, or I can consider in between where most of the power, like the 3 dB point here. This is just different convention. I am considering the entire lobe in the NRG encoding. So that would give me if, and the second relation that I have to use is, we know that C is equal to nu lambda, or del nu is equal to C by lambda square del lambda. Let's put on to get rid of the negative signs, and this is how I am able to correlate my spectral width with delta lambda, because in my calculation it was nanometer. The dispersion was in terms of nanometer, where here if I here this is given is 10 Gbps, 10 gigabits per second. So I need to convert that spectral width, this spectral width, in terms of frequency. And after I have done that, I will easily put it into the formula. And after that, the accumulated dispersion is similar as in the previous case, which is del T is given by dl delta lambda. Or it can be written as TL. In the last we had found that TL is equal to what did we find? We found that del nu is equal to c by lambda square del lambda. So del nu lambda square by c is equal to del lambda. Now because this is a 10 gigahertz signal and I'm considering on both sides of the load, this would be del nu lambda square by c, which would be dl. Del nu would be 20 gigahertz centered around 1540 nanometer, and c is just the speed of light. Now if you substitute all the right units and everything, you will get a dispersion of minus 252 picosecond. Now the question is, what should be the dispersion parameter to compensate the accumulated dispersion in the fiber described in question number 3 at 1540 nanometer for a DCF fiber, dispersion compensating fiber of 10 kilometer length? What is given to us is that, let's say I had a, let us picture it this way, I had a pulse like this and went down an optical chain, and this pulse had a bunch of different frequency components, and this is my fiber. Now what happens on the other end, because these different frequencies see different refractive index, they slightly broaden. So these are slightly broadened. Now this is a normal fiber where dispersion is happening. Now what this question is telling me, if I can put a shorter, so this length was 100 kilometers. Now it is asking me what should be the length of the second fiber that I am putting of length 10 no, it is asking what should be my decompensation factor for the dispersion such that a 10 kilometer fiber cancels out this broadening, such that your pulse on the other side looks exactly like this. Okay. Now we saw from the last question that accumulated dispersion is given by d1 L1 delta lambda, and if there is dispersion I want to compensate for it. So dispersion d1 over the range L1 plus dispersion d2 over the range L2 should be 0. In that case it will give me d2 is equal to d1 L1 by L2 with a minus sign, and this gives me 159 minus 1 5.94 picosecond nanometer kilometer into 100 divided by 10, which is 159.4 picosecond per nanometer per kilometer. So if we put a fiber on the last 10 kilometers, or not the last, if we put a fiber after this 100 kilometers, another 10 kilometer with a dispersion coefficient of 1.59, we would be entirely eliminating the effect of dispersion that was caused by this fiber. Now the same question is asked for 10 Gbps signal. Now you remember that in the last expression it was just d1 L1 is equal to d2 L2 with a minus sign. We did not use del lambda both sides because they cancel each other. They are cancelled from both sides. So that is why this parameter will not change again for whatever frequency. If you have 10 gigahertz or you have to have 1 gigahertz, 100 gigahertz, it does not change. Another way to think of it is, if you have a wide enough response, if you have a bigger spectral content in this and it spreads by more, the same thing will happen on the compensating fiber side as well, because if it is stretching more in that medium, it will compress. If I put it in the negative sign, it will compress more as well. So then you would just be left with the same pulse again. So that is why the encoding scheme does not matter. What is the bandwidth of the signal in this case does not matter. So the answer would be same as the previous case, which is 159.4 picosecond per nanometer kilometer. Now let us look at the next question. Next question is a DWDM, dense wavelength division multiplexing transmission system has a channel spacing of 100 gigahertz. Find the number of channels that can be used in 1530 to 1560 nanometer band. This band has a name. This band is called C band or conventional band. 1630 to 1530 to 1560. If we number the bands sequentially from lowest to highest possible wavelength, find the wavelength spacing between the first two bands and the last two bands. Now, we looked at this formula earlier, right, where it was delta lambda C by lambda square is del mu. So you see, depending on where you are on the wavelength, where is your central wavelength, the delta lambda would be different for the same d nu. So let us look at it in this way. I know delta lambda is lambda square by c del nu. If I am at 1530 nanometer, and my del nu is 100 into 10 raised to the power 9. 1 giga is 10 raised to the power 9. Let me just find my calculator to do this. This is given as 1530 nanometer squared divided by 3 into 10 raised to the power 8 into 100 gigahertz. Which turns out about 7.803 into 10 raised to the power minus 10. So I know that the difference spacing between the first two bands would be, this is 0.78 nanometers, because you take this on the other side and you have 10 raised to the power minus 9. So this would make this option to be correct. I mean, we can do this and we can show that it is slightly different. Let's do that as well. You know, delta lambda is lambda square by c del nu 1560 into 10 raised to the power minus 9 whole square by 3 into 10 raised to the power 8 into 100 gigahertz. Let me just go and modify that one wavelength from 1530 to 1560 in my calculator, and this gives me 8.11 into 10 raised to the power minus 10, which is 0.81 nanometer, which was here in this case. So although if you're just eliminating the options, just with the first one we could have figured out that this is the correct answer, but for the sake of completion we are doing both of them. Now let us look at the next question. The next question is, given dispersion of 17 picosecond per nanometer per kilometer at 1550 nanometer. Now this is a reasonable dispersion number that is found in the SMF28. Now SMF28 is single mode fiber, and 28 is, so this is just the part number for commercially deployed fiber. Now it is given D is equal to 17 picosecond per nanometer per kilometer for 1550 nanometer. Find the phase mismatch generated for the first higher frequency content of WDM channel spacing 50 gigahertz and 100 gigahertz. Now we have been given two different channel spacing, and we have to find the phase mismatch because of this dispersion. Now we know that the phase mismatch beta 2 is related with del beta in the phase frequency mismatch, which is delta beta, is related to beta in such a way that beta 2 omega square, where omega is the frequency, which is 2 pi nu, angular frequency, And we also know that beta 2 is related by d lambda square by 2 pi c. So it is just, if we start doing back substitution, now we are given 17 picosecond per nanometer kilometer, and I have my lambda square by 2 pi into 3 into 10 raised to the 8 meter per second, and my lambda is given as, should have replaced my lambda here as well, which is given as 15 to 10 raised to the minus 9. This number, when you do the math, it will come out as 2.168 into 10 raised to the minus 26 seconds square per meter. Now after I have this number, I can easily go back for 50 gigahertz spacing. Omega is 2 pi 15 to 10 raised to the 9, and that would give me delta beta is equal to beta 2 omega 2 square, and when you do the math, it will come out as 0.0021 radians per meter. Now if we have for 100 gigahertz, let us go and look back at this formula. There is nothing in this that depends on the spacing itself. So the beta 2 is independent of the spacing in this case. So what will happen is only my omega will change. So omega 100 gigahertz is given by 2 pi 100 into 10 raised to the 9. Therefore, you simply calculate del beta can be through. Now if omega has been doubled and its dependence is square of it, you can easily see that this will become 4 times. So this will become 0.0084 rad per meter, because if omega nu is to omega old, and in some relation there is f of omega is omega square, therefore f of omega nu is equal to 4 times f of omega old. This is just a simple mathematical relation, and you'll see that from this expression we can see that the phase mismatch is higher for the 100 gigahertz by a factor of 4. Now let us look at the next question. The next question is, dry fibers have an acceptable loss over a spectral region extending from 1.3 to 1.6 micrometer. Estimate the capacity of a WDM system covering this entire region. With 50 gigahertz channel spacing, consider each channel is modulated by 10 gigabaud 16 form data with Nyquist pulse shaping. Now, this can be understood as 1.3 micrometer. We have to utilize the relation C is equal to nu lambda for 1.3 micrometer. Nu 1.3 micrometer is C by 1.3 into 10 raised to the minus 6, which from my notes it comes out to be something around 230.6 terahertz. Similarly, mu 1.6 micrometer, it turns out to be something around 187.3 terahertz. Now that I have both these channels, so what essentially I have my starting, which is 187.37 terahertz. I have my end, which is 230.6 terahertz, and I know that the channels in between, from given in my question, they have to be 50 gigahertz separated. So all of these bands that I am dividing in there, all of these are 50 gigahertz separated. Now this can easily be done with, you just subtract these two and figure out how many items there are, and you will see that there are 864 channels the way to do this is 230.6 terahertz minus 187.3, which gives me TEL frequency is 43.3, and which is divided by 0.05. Now this is almost in terahertz. That turns out to be 864. Now each 864 is 10 gigabaud per sample and 16 quam. That means 40 Gbps. 10 gigabaud, 16 quam is 40 Gbps. Remember our baud rate and bit rate conversion. So our total information carrying capacity is 864 into 40 Gbps. 864 into 40 Gbps, which gives me something about 34560 Gbps, which is something like, should not have put that decimal there, .56 Tbps. So if I have a 50 gigahertz spacing, you see that I cannot transmit a data of 34.56 on the same fiber. Now let us look at the question. Now again we have been given the C and L spectral band cover a wavelength of 1.53 to 1.61 micrometer. How many channels can be transmitted using WDM when the channel spacing is 25 gigahertz? So this can be solved in the similar way, where you take lambda and then you convert it into nu using the relation C by lambda, and after that you have lambda max, which in this case will be lambda 1.53 minus lambda 1.61 divided by 25 gigahertz. And this will give you total number of channels. Oh, this is something, I guess if you did not notice, I illustrated 1300 nanometer, and in the earlier case we had 1600 nanometer. And when I converted this back into frequency, this was 230 terahertz and this was 187.3 terahertz. So that means when I'm doing it in the wavelength picture from the origin, it would look something like 1300 would come here and 1600 would come here. But if I'm doing a frequency picture, this gets flipped around. So first in the frequency I have 187.3, which is 1600 nanometer, and then I have 230 terahertz, which is 1300 nanometer. So this is just something not to get confused about. This is there because frequency and wavelength are inversely proportional to each other. Now the last question that we'll be discussing today is, what is the effective bitrate distance, bitrate product when WDM signal covering two bands using 10 Gbps channel center at 1550 with dispersion of 17. So there are two ways our signal can be limited. One is bandwidth limitation. The second is dispersion limited. Or rise rate. In this case, we are considering that it is dispersion limited. So that would mean that whatever my signal is going through, that is being limited by the entire dispersion that is happening in the pulses in through the fiber. And we can easily calculate this by 1 by d delta lambda. So we know that from our experience, we know that 50 gigahertz is equal to 0.8 nanometer. This again comes from the relationship where del nu lambda square by c is del lambda, and lambda is 1550 nanometer. So for a 10 Gbps, this becomes 80 picometer. So this would be given by 1 by 30 picosecond per nanometer kilometer into, actually sorry, this is 50 gigahertz is 0.400 gigahertz is 0.8 nanometer, so 10 gigahertz is 80 picometer. And when you do this multiplication, you will arrive at 735 megabits per second kilometer. Now in the question it is given that using 2 bands, so that means the effective data rate using 2 bands, effective data rate is equal to 2 into 735.2 Mbps, which is something like 1.43 Gbps kilometer, because this is bandwidth distance product. And with that, we have looked at the tutorial questions that were shown. If you have any more questions, or if you have any clarifications, if you have any doubts and you would want clarifications on that, please post in the forum and I'll reply to that. Thank you.